Okay. Hi everyone. Today I will introduce our project, which is a HOS accelerator for the Pangenome graph visualizations. Okay, I will first introduce the background and motivation, and then demonstrate our algorithm and the implementation, including a simplified baseline on CPUs and HOS synthesizable baseline that would require a series of modifications to make it synthesizable in Vivado HOS tools. And also we apply a series of optimizations, including power law approximation, on-chip storage, and data type customization to reduce both its latency and resource utilizations, and to make a larger design fit on the Z board due to its limited VRAM. And also we have some future works to do, including the optimization directives and to make it scalable to larger devices. Okay, so first I will introduce a little bit background on Pangenome graphs. The genomes are very long strings with A, T, C, and Gs, and there are lots of common words between those genomes. And Pangenome graphs are constructed to represent the relationships between the genomes. And each DNA words here represent the nodes in the graph, and genomes are the path stepping through series of nodes. And in the Pangenome graph, we are very careful about the variations, which are the bubbles between different genomes. So in this graph, you can see that there are several variation loops here that we want to demonstrate it in the process of 2D visualizations. So that's why we want to visualize the Pangenomes. Okay, so then I will introduce the algorithm. First is the iterative algorithm. You can see it in this GIF figure. And it is an iterative process, and the input is the Pangenome graph, which consists of the nodes and edge, and the output is that we need to assign the coordinates for each visualization nodes. Okay, so in more details, the algorithm is called the graph join by stochastic gradient descent. So actually, for each iteration, we choose two nodes, which is node pairs in the 2D visualization space, and we have a ground truth distance in the graph, which is Dij, and also we have two coordinates in the visualization space, which is xi and xj, and we can have a distance in the visualization space. And here we want to match the distance in the coordinate space to the ground truth distance. So what we do here is to compute a delta and to add or minus this delta distance to the current visualization positions to make it closer to the ground truth distance. So following this iterative process, so this is a pseudocode of the whole algorithm. There is 2 4 nested loops, and following this iterative process, we can finally get decent results for the Pangenome graphs. And for the implementation, first we need to get a simplified baseline on CPUs, as this whole algorithm is a real algorithm that is used in the biological field. So initially it's implemented in a general libraries that would require lots of dependencies. So first we need to have a simplified baselines that would involve with lots of modifications. But the result is that we can get a simplified version, and the layout result is correct, and also we can get even higher performance compared to the original library, which is called ODGI here. And then the simplified baseline on CPU cannot be directly synthesized in HOS, so that would need several modifications involved with memory allocations. We need to statically allocate memory. And also we need to create our own pseudo-random number generator module. And also for the probability distribution, we need to create our own module to do that. Yeah.
So we did some optimizations to approximate the original power law distribution. The original algorithm generates a pseudo-random number based on the power law distribution, which we call PLD. A naive PLD will contain the power function, which is very expensive to synthesize in HLS. However, we can try to approximate the PLD with lookup table-based sampling. To generate a PLD-based random number, we choose a uniform distributed pseudo-random number, and then it is compared with predefined lower bounds and upper bounds. Then the PLD output is determined by the range in which the pseudo-random number falls. The following figure illustrates how to sample numbers 1, 2, 3, 4 with a PLD using a power of 2. You can see that each of the 4 ranges can be predefined offline. For example, in this figure, if we want to sample 1, 2, 3, 4 with a probability of 8 to 4 to 2 to 1, we can divide the uint max, which is the maximum integer value in C++, by 15. And if the generated pseudo-random number with a uniform distribution, if it falls in the first 8 ranges, so we divide the uint max by 15 ranges. So if it falls in the first 8 ranges, then we will assign it with a value of 1. So if it falls in the next 4 ranges, then we will assign it with a value of 2, and so on. So the naive PLD consumes about 1/4 of the total resource for each type after HLS. And with the proposed LUT-based sampling, we can reduce the resource consumption of PLD significantly, and the cost actually becomes negligible, as shown in the following table.
Okay, so let me introduce our next optimization strategy, which is to avoid the data transferring by storing all data on chip. So because for this application, when we fix a data set, all the graph information is also fixed. So we can directly put them in the on-chip memory on the board instead of uploading them to the board through FIFO whenever we run the program. And here, the following tables show the synthesis results. You can see that from the first table, we can see slightly reduction for this storing on-chip optimization, as well as the latency reduction. And in the second table, which is about the execution time, there is a surprising result here that if we use the O3 compiler optimization on CPU, we can actually get significantly better results than the deadboard optimization. So that's a reason why we didn't apply this strategy to our final design. And one thing to notice here is that these results was on the tiny toy example. If we try to apply this on a larger data set, it will affect the bitstream generation process, so that the generalization will take forever. So yeah, we didn't actually use this in our final design. And then we have our next optimization strategy, which is data type customization. So we are here use 14-bit instead of the default 32-bit for our data types, which can save a lot of memory usage from the boxes here. You can see that the optimized latency is significantly reduced compared to the baseline. And also, we can get we can get 1.7 speed up improvement on FPGA if we compare the Z-board result with the baseline. So, but actually we are not outperforming the CPU baseline. And that is because we haven't successfully implemented the parallelism execution, which we'll be introduced in the next slide.
Okay, so we still have some future work to do. First is about the optimization directive. So for now, we haven't successfully inserted the unrolling and the pipelining directives into the design due to the random memory access. That is, it's not the same as the standard convolution or matrix multiplication that we can have a fixed pattern to access memory. Here we have a random distribution for each memory access so that we cannot directly tell the synthesizer which which part of the memory we want to utilize for each unrolled loops. So we would need other strategies to support it. And also we want to run it on the larger devices because the real data set can just fit into the Z-board due to the limited VRAMs on the Z-board. So larger devices are required for applying the array partition and unrolling optimizations, and also can help us to support larger data sets. Yeah, so that's all. Thanks.